Hello and welcome to Week 9, Part 2 of EGM310, Electromagnetic Radiation. In this lesson, we'll cover the basics of electromagnetic radiation, the main tool we use to gather information in remote sensing. In the previous lesson, we discussed how, in a way, we've all been doing remote sensing for years. Our eyes, ears, and nose all collect data about the world without touching it. They are remote sensors. In particular, our eyes use light to sense the world around us in a very similar way to how we collect remote sensing data. The light that we see is a type of electromagnetic radiation, and we'll talk more about what we mean by electromagnetic radiation in a minute. For most remote sensing, we use electromagnetic radiation to observe things. But how should we think about or picture light or electromagnetic radiation? Please note that in this lesson I'm going to be using light and electromagnetic radiation interchangeably, and we'll learn why that is a bit later. Over time, physicists developed two main theories for how light behaved: the particle model and the wave model, based on the different phenomena or properties that they observed. So, is light a particle or is it a wave? The table to the right here lists the different properties and indicates which of the two models can be used to explain each one. Both models can explain reflection and refraction, but only the wave model can explain the properties of interference, diffraction, and polarization. But the wave model can't explain the photoelectric effect, whereas the particle model can. So the answer to the question, is light a particle or is it a wave, is it depends. The reason why this is well outside of the scope of this course, but if you're interested, there are more links at the end of the presentation or in the description below that go a bit deeper into the topic. Electromagnetic radiation is a self-propagating wave. By self-propagating, we mean that, unlike water waves or sound waves, electromagnetic waves travel through space without any external influence. As the name suggests, electromagnetic waves have both an electric component and a magnetic component. One of the major lessons of 19th century physics is that a changing electric field induces a magnetic field and vice versa. This is the principle behind, among other things, induction stovetops and electric motors. So an electromagnetic wave moving through space has both an electric and a magnetic component, usually denoted E and B, respectively. The electric component is moving and oscillating in one plane, in this example, the XZ plane, while the magnetic component moves and oscillates in a plane at a 90-degree angle, in this example, the XY plane. Like any other wave, an electromagnetic wave has different attributes or properties. It propagates at a certain speed, usually denoted c. In a vacuum, the speed of light is about 3 times 10 to the 8th meters per second. In other materials, such as in Earth's atmosphere, it drops by about 90 kilometers per second, or about 0.03% slower. We can also define the wavelength of an electromagnetic wave as the distance between one full cycle. This can be measured between successive peaks, as shown here, or between successive troughs, or the distance between points where the electric component is 0. Another important property is the frequency, usually denoted f, of the wave. This is the amount of time it takes to go through a single cycle. The wavelength and frequency are both related to the speed of the wave according to this equation here. The speed of the wave is just the wavelength times the frequency. Other properties of electromagnetic waves include the phase, or fraction of the cycle. As you might have guessed, this is usually defined between 0 and 2 pi, or 0 and 360 degrees. Finally, there's the amplitude, which is the height of the peak or the depth of the trough, and this is associated with the brightness or intensity of the light or of the electromagnetic radiation. The table here lists the different components that are labeled on the slide and their respective units. Light is a transverse wave. That is, the electric and magnetic components of the wave oscillate perpendicular to the direction of motion. We can therefore define or specify an orientation for this oscillation called the polarization of the wave. By convention, we normally define the polarization using the electric component of the wave. In this top example, the wave is vertically polarized. The electric field is propagating along the x-axis, oscillating in the xz plane. In the second example, the electric field is still propagating along the x-axis, but it is oscillating in the xy plane. We would say that this is a horizontally polarized light wave. Light can be polarized at any arbitrary angle. It can even have a circular or elliptical polarization where the plane is rotating around the direction of motion. And just as a side note, the fact that electromagnetic waves have a polarization is used frequently in microwave or radar remote sensing. Because of this, we can actually construct filters that will only allow through light at a specified polarization. This is especially useful for radar remote sensing, where the polarization of the radar signal partly determines what we actually see with the signal. We can also use this to create glare-reducing polarized sunglasses. Remember that I said that light can behave as both a particle and a wave. We've seen how we can describe light as a wave, and now we'll take a look at the particle model. In this model, light is a particle called a photon that has a particular energy Q. Another of the big discoveries of 19th and early 20th century physics is that objects, which is to say atoms, can only absorb and emit energy in discrete units called quanta or photons. And if you're wondering, yes, this is where we get the term quantum mechanics. The amount of energy, then, that a photon has is directly related to its frequency by a constant known as Planck's constant. Using what we know about the relationship between the frequency and wavelength of light, we can rewrite this using the equation on the bottom of the slide here, with the table here showing the units of the different variables on this slide. So the energy contained in a photon is inversely proportional to its wavelength. Put another way, longer wavelengths mean lower frequencies mean lower energy. Conversely, shorter wavelengths mean higher frequencies mean higher energy. For remote sensing, this also means that longer wavelengths are harder to detect. We need more photons at lower energies to strike our sensor in order to register a signal when compared to higher energy photons. All matter in the universe that has a temperature above 0 Kelvin, or minus 273.15 degrees Celsius, emits some electromagnetic radiation. The amount of radiation that is emitted, also called the radiant emittance, strongly depends on the temperature of the object. For an idealized object called a blackbody that perfectly absorbs and re-emits all of the energy that falls on it, the radiant emittance is directly proportional to its temperature raised to the 4th power. The equation here is known as the Stefan-Boltzmann law. So relatively small increases in temperature lead to large increases in radiant emittance. In reality, most objects aren't perfect blackbodies. Instead, they emit some fraction of the electromagnetic radiation that blackbodies do. We can measure how well an object approximates a perfect blackbody via its emissivity, which is defined as the ratio of its emittance to that of a blackbody with the same temperature. And again, we have a table here that shows the different units for the variables on the slide. Starting to put all of this together, we see that objects with higher temperatures have higher energy, and the electromagnetic radiation they emit will have a higher frequency or a shorter wavelength. This also means that the color of electromagnetic radiation that an object emits will change with temperature as well. The plot here shows how an object's radiance, or the amount of energy emitted, varies with both wavelength and temperature. Note that this is a semi-logarithmic plot. The steps on the y-axis here represent an increase of 1,000, while the steps on the x-axis go from 100 to 1,000 to 10,000 and so on. Cooler objects, shown as darker lines on the plot, have a lower overall radiance, and the wavelengths they emit most at are much longer. As we increase in temperature, going up in color, We also increase the overall radiance. The peak gets higher and higher, and we shift the peak of the curve towards lower wavelengths. In space, our sun appears mostly white because it emits fairly evenly across the wavelengths that we can see with our eyes, though our atmosphere changes this slightly. And if we look at this curve here, corresponding to about 6,000 Kelvin, we see that the amount of radiation emitted across the visible wavelengths is fairly even, which gives us a fairly white color. Wood fires at about 1500 Kelvin have much stronger emittance in the red portion of the visible wavelengths, and so we see that they have more of a reddish orange color. The human body at about 300 Kelvin hardly emits at all in visible wavelengths. It's mostly in the thermal wavelengths. We can calculate the dominant wavelength that an object emits, which is also the color of its maximum radiance, using something called Wien's displacement law. I think we've already had enough equations in this lesson, so that's one for you to go look up later. Electromagnetic radiation comes in a large range of possible wavelengths or frequencies, which we call the electromagnetic spectrum. As we can somewhat arbitrarily divide the spectrum into regions of wavelengths with similar enough properties. As you can see here, the light that we can see with our eyes, known as visible light or visible electromagnetic radiation, makes up a very small portion of the total electromagnetic spectrum, with wavelengths between about 400 and 700 nanometers. Just below visible light, so shorter wavelengths than what we have for visible light, we have ultraviolet light, with wavelengths between about 10 and 400 nanometers. Above the visible spectrum, so slightly longer than 700 nanometers, we have what is called infrared light, followed by microwaves, and then radio waves, and then long radio waves. These can have wavelengths of over several kilometers in length. Each of these different regions has its own properties that we can use to study different things. As I mentioned, the divisions are somewhat arbitrary, and different users may have different definitions or different preferred units. Electrical engineers and people who do microwave remote sensing tend to prefer hertz, which is units of frequency, while people who do optical or thermal remote sensing tend to prefer units of wavelengths. The table on the left-hand side of the screen lists a number of different portions of the electromagnetic spectrum that we often use for remote sensing. You can look this over and see the different sort of definitions here. One thing to think about before the next lesson: why haven't I listed any wavelengths that are shorter than visible light? So why is there no ultraviolet light that we tend to use for remote sensing? As we've seen in this lesson, electromagnetic radiation, or light, has the properties of both a wave and a particle, which is only a small part of what makes our universe such a strange and wonderful place. The energy of electromagnetic radiation depends on its wavelength or its frequency. Higher wavelengths or lower frequencies mean less energy, and vice versa. All objects with a temperature over absolute zero emit electromagnetic radiation, the amount of which and color of which depends on the temperature. Finally, we can think of electromagnetic radiation as existing on a spectrum of wavelengths or frequencies and divide these up depending on their properties. As you can read more about the topics that we've discussed here in the two textbooks, Lillesand, Kiefer, and Chipman, Chapter 1, or Campbell and Wynne, Chapter 2, or read more about it from the Natural Resources Canada Remote Sensing Tutorials. I've also included links that cover some of the extra topics that we didn't get into, like the photoelectric effect and the ultraviolet catastrophe, which goes into some more detail about blackbody radiation and the history of its study. That's all for this lesson. I hope you found it interesting, and if you have any questions, please don't hesitate to email me or post them in the discussion forum on Blackboard. Bye!